Okay, so this is the continuation of session 11 because we had an interruption with the last recording. We only have the two last slides. So the solution of the Klein-Gordon equation is the sum of plane waves. So if you have phi, a wave that is defined by the exponential of minus omega t, exponential I, of k, x, y, and z. K here is the wave vector. So it is equal to e to the power I, k mu, x mu. If you make the derivatives of phi del square, the second derivative of phi with respect to t, so you get minus omega squared exponential of I kx, so it's phi. So minus omega squared phi. The second derivative of phi with respect to x squared is also equal to minus k squared phi. So if you put this in the Klein-Gordon equation, you will get minus omega squared over c squared plus kx squared plus ky squared plus kz squared plus mu squared, which is equal to 0. So omega squared is equal to c squared times kx squared plus ky squared plus kz squared plus kz squared plus mu squared. So so omega, the angular frequency would be equal to plus or minus c times the radical of kx squared plus ky squared plus ky plus kz squared plus mu squared. Let's take a practical example. If you have a wave that is defined by exponential of I omega t minus kx, and you know that the exponential of I something could be written as the cosine of omega t minus kx plus I sine of omega t minus kx. So the cosine of omega t minus kx and the sine of k of omega t minus kx are both solutions to this Klein-Gordon equation. So if you draw it here, if you put the cosine in the red line as in the red curve, and the sine here on the blue curve, so for t equals 0, you see that you have a difference of phase or a phase of 90 degrees. Okay, so this is the end of this session. We will continue with with more and more such sessions on the next days.